Welcome back to the Intro to Machine Learning class. In this lecture, we're going to discuss neural networks. So far, we've learned about the perceptron. It's a linear model in that it can create a linear decision boundary. We were able to solve a couple of problems with the perceptron, notably the and or logical functions. And by solve, I mean get 100% accuracy on the training data using the perceptron. However, there's other simple problems that the perceptron cannot solve. We cannot get 100% accuracy on this training data for the XOR logical operation. So this leads us to neural networks. Neural networks are simply stacked perceptrons with additional nonlinearity. This is what they look like. In this example, we have 3 layers. We have the input, the hidden layer, and the output. So this gives us 2 sets of weights. The first set of weights is between the input and the hidden layer, and the second set of weights is between the hidden layer and the output. Any layer between the input and the output is called a hidden layer because we don't have any idea what those values should be, unlike with the input where we have the input, and unlike with the output where we have some label that we want to achieve. This is a fully connected network. That means that every node is fully connected to every other node in its output. So it's feed forward. So all of the hidden nodes are not connected back to the input, but all the input is connected to the hidden nodes, and all the hidden nodes are connected to the output. I didn't draw all the connections here because that would be tedious and unnecessary. So the ... kind of indicates that it continues in a fully connected fashion. We use kind of a strange notation for these weights. So now that we have weights at the first layer and at the second layer, we need some sort of superscript. Here we have 1 and 2 to indicate which layer we're on. And then on the first layer, you're going from some input to some hidden. And you can go from input 1 to hidden 1, input 1 to hidden 2, and so on. So we have this W1 ij, and I is the input and j is the output. So from x1 to h2 would be w1, 1, 2. Where we're coming from and where we're going to. Now for the second layer, we have w superscript 2, and then we have j, because it's the j matches the same as the first layer, and it corresponds to the hidden unit we're coming from, and it's all going to the output. So there's no going to, it's just going from. The output is then w2 dot product with h. So both w2 and h are vectors here. And each individual hidden unit is the dot product of the weight vector associated with that hidden unit. So all of the weights coming into that unit, so that colon indicates all of the inputs coming in. And then you dot product that with the inputs, x. We take that dot product for the output and we just turn it into a summation. So it sums over all j, all hidden units. And we have wj2 hj. So if we combine those two things, if we combine the hj with the output, we actually get this expression where we have the sum over all j, w2j times w1 colon j dot product with x. All I'm doing is substituting here, so there's no need to panic about the math. I'm just substituting in the equations from here. So this is just a linear combination of linear functions. So we took the linear functions from w1 dot x, and we just applied another weight to that. So we're really not doing anything interesting. We're just doing linear combinations of linear functions, which end up being more linear functions. So how are we going to solve this XOR problem or any nonlinear problem if all we have are linear combinations of linear functions? This right here is just a bunch of stacked perceptrons. Now we add the nonlinearity, which makes a neural network special. So here we have the hidden unit equals A, which is some activation function. So it's not some constant A, it's actually some function that is then applied to W1 colon J dot X. Okay, and that's any sort of nonlinear function. What kind of nonlinear functions do we use? We'll talk about that in a minute. So you can actually apply a nonlinearity at every layer. So you can apply it at the hidden layer and also at the output, and they don't have to be the same. So here I have A1, which is some nonlinear activation function being applied to the hidden layer. And then I have A2, which is a nonlinear activation function being applied to the output. What kind of nonlinear activation functions do we use? One example is a sigmoid, which we've dealt with before, which has this shape, and we can just apply that to our hidden units or to our output. Another option is the tan H function, which just looks like this in comparison with the sigmoid. So instead it ranges from -1 to +1, whereas with the sigmoid it ranges from 0 to 1. What's most commonly used is the rectified linear unit, or ReLU. All it is the maximum of some value or 0. Okay, so it takes all negative numbers and makes them 0, and then if it's a positive number, it leaves it as is. So it looks just like this. Okay, we have our model. Now, how do we actually learn these weights such that they do something that we want? Well, we use backpropagation, which is just a fancy term for gradient descent plus the chain rule. What's our loss function? You can use a lot of different loss functions, but right now we'll focus on Euclidean loss. So we're going to do squared error here. We have y is the truth and y hat is the prediction. And we want to minimize the difference between those two squared. In terms of what we showed a few slides ago, this is going to be y minus out. So out is going to be our prediction. And expanding this by just putting all of the terms in there, out is actually, without the activation function, it's W2.H. And so we expand that here with the dot product just being that sum. If we want to update the weights at the second layer, we have to take the derivative of the loss with respect to W2. So let's look at the particular weight W21. So that means it's the connection between the first hidden unit and the output unit, H1 to out, okay? When we take the derivative of this loss function here with respect to W12, we get the above equation, which is -2 H1 times y minus out. And this generalizes to every Wj. Instead of H1, we now have Hj, and this is going to be our derivative for each one of those. Okay, what does this actually look like? Well, we can take the derivative of L with respect to out, because out is what has H in it, and we get -2 times y minus out. And then we can take the derivative of out with respect to a particular W2, and we get Hj. And if you just multiply those two together, you get the equation at the top. So this is the chain rule. Instead of expanding this entire function and then taking the derivative, which can get very messy, you just take the derivative of each part and then multiply them together. Now let's do W1. This gets a little more complicated because there's a little bit more going on. So we have the loss, we have the out, and we have Hj. So we know that we need to go all the way from the loss down to W1 in order to take the derivative. So first we take the derivative of the loss with respect to out, which is going to be the same as before. Then we take the derivative of out with respect to Hj, because Hj is what has W1 in it. And then we take the derivative of Hj with respect to W1, and the particular W1 would be Ij, and the result is Xi. We multiply all those together. And that gives us the derivative of the loss with respect to that particular W1. So what if we have an activation? If we have an activation, the only thing that changes is here in the derivative of the out with respect to W2. And here we would have A prime, so the activation prime. So you take the derivative of the activation, and then you still multiply it by the derivative of the inside, which is hj. Similarly, if we have an activation at the hidden unit, we would take the derivative in the part where we have the derivative of h with respect to w1. And so then we just have these additional derivatives. It's all part of the chain rule. So it doesn't really add any additional complication as long as you can easily take the derivative of those functions. So backpropagation is just gradient descent plus the chain rule. So we just talked about the chain rule, so we have to do the gradient descent part. In order to update W1s, we just take the old W1 and we subtract some learning rate, eta, times the derivative of the loss with respect to that W1, and similarly with W2. Now B is going to be the same. There's just going to be a slightly different derivative because there's no x associated with B. The x associated with B is 1. So all the derivatives would be the same, and you would just get rid of the x that's in there. How do we initialize? With the perceptron, we initialize with w and b all equal to 0. I'm making the assumption that b is kind of lumped in here with the w's, and I'm going to kind of ignore it for now. What happens if we initialize our neural network with 0? Well, if we have these nonlinearities, right, we apply them, and we end up with the hidden units now have the value of a1 of 0, and the output is 0. We assume there's no second activation function. So what happens with our derivatives? The problem lies in the actual update. Here we have those derivative functions that I gave you before, and we're trying to calculate what's happening with W2. The problem becomes that the derivative with respect to every W2 is going to be the same because all of the hidden units have the same value. So this derivative of the output with respect to W2 is going to be the same for every single W2. So W2 is going to get updated the exact same way for every single one. And now we look at W1, and W1 is going to get updated with 0. So the issue here is that if we start with all zeros or all of the same number, we're going to update in the exact same way. So we're going to learn a really stupid function. We're going to learn a function with a bunch of hidden units, but they all do the same thing. So what we want to do instead is initialize randomly. If we initialize with random small numbers, usually between -1 and 1, we can get away from this weird local minimum. So neural networks are a model. And the algorithm is backpropagation. So the algorithm to train the neural network is the gradient descent plus the chain rule. And that's it. They're pretty scary. If you look at all the math out of context, it seems very frightening. But if you just think about we're in some higher dimensional space and we're looking at some function and all we're trying to do is get to the minimum of that function, and the function is the loss. So if you think about it that way, it's a very simple concept and there's a lot of math behind it.